Okay, hi everyone. This is going to be a video for lesson 2.7 part 1, which is about rates of change. And today we're going to be calculating and interpreting the slope of tangent lines and secant lines. I'm just going to highlight those two. So first we're just going to go over what a tangent line is and what a secant line is. So let's say we have a function which on my screen is green. I'm just going to label it f of x in both boxes. So let's say I have a function f of x. Then the secant line is the line you draw between any 2 points on your curve. So for example, let's say we're looking at these 2 points. The secant line would be this straight line shown in blue here. Okay, and that has special meaning. The secant line, the slope of the secant line describes the average rate of change of that function between those 2 points. Okay. In contrast, a tangent line is just looking at one specific point, and if you draw a straight line that matches the shape of the curve at that point, then that's called the tangent line. And the slope of the tangent line has special significance. It describes the instantaneous, not the average, the instantaneous rate of change at a specific point. Okay. This specific point is going to have, we're going to be calling it x equals a in our formula. So I'm just going to label it a in both graphs. Okay. Let's talk about the secant line first. So to find the slope of a line, you just do the rate rise over run, or change in y over change in x. I'm going to label the points slightly differently though, but we're going to use that same formula to calculate the slope. So the first point is x equals a, and then the second point we're going to label as a plus h. Okay. So the distance between those would be h. So that's our run between the 2 points, or change in x. Okay. And then if the x value is a, then the y value at that point would be f of a. And at a plus h, the y value would be a plus h. And so the rise between those 2 points would be f of a plus h minus f of a. Okay, so to calculate the slope, you would just do the rise over the run, or change in y over change in x. So the slope formula is shown down here. So this is no different than the slope formula you've been using for years. Just the points are labeled differently, but it's the same formula. Okay, so that's the slope of a secant line. So we already know how to calculate that. The slope of the tangent line is different though, because we don't have 2 points. So we can't do change in y over change in x. We need the help of the secant line actually to help us understand how to calculate the slope of the tangent line. I'm going to show you a graph in Desmos. Let's just say this function was in green here. This is my function, and these are the 2 points shown in black. Okay, this is a, and this is a plus h. Okay, and I'm going to just show what the tangent line looks like there. That's what we want to know, what the slope of that red line is. And here's the secant line in blue. Okay, the lines are different at this moment. The blue line would have a larger slope than the tangent line. Okay, but let's see what happens as we bring these points closer and closer together. On the left here, I have a value h. I'm just going to make that smaller and bring the points closer together, and we'll see what happens to the 2 lines. So watch the red and blue lines as I bring these closer and closer together. They get closer and closer, and at h equals 0, they're actually the same line. Okay, so again, when they're far apart, the lines are quite different. And then as we bring the points closer and closer together, as h approaches 0, these 2 lines approach each other, and the slopes are equal at h equals 0. So you might think, okay, cool, we can just use the same formula but plug in h equals 0. But the problem with that is that that would mean dividing by 0. So what we have to do instead is take the limit as h approaches 0 of that secant line formula. Okay, so it's the same formula, it's just that you take the limit as h approaches 0. So we're going to do an example. we're going to find the equation of the tangent line to the curve y equals x squared minus 1 at the point 3, 8. Okay. All right, so I'm just going to write down my tangent line formula. It's just shown above in highlighted in yellow. So the tangent line formula is limit as h goes to 0. So as those 2 points come closer together, f of a plus h minus f of a all over h. And we're particularly interested in this point 3, 8. So the x value we're interested in is 3. Remember, in our formula, a is the x value that we are concerned with. So in our case, it's 3. And so f of a would be f of 3, which if you plug 3 into the equation, you get 8. So I'm going to plug in our specific point into our little slope formula here. So f of 3 plus h minus f of 3 all over h will be the same as limit h goes to 0. So f of 3 plus h, we have to use our combining functions from chapter 1. So I'd plug 3 plus h into the formula. So I'd get 3 plus h squared minus 1. And f of 3 is 8. And h we can just leave in the denominator. And now we have to use some skills from section 2.3 to solve this limit, because right now I cannot plug in h equals 0. That would give me 0 in the denominator, which is undefined. So I'm going to try expanding, which was one of our strategies that we learned for solving limits. So if I expand that bracket there, I'd get 9 plus 6h plus h squared. And I'm going to combine the -1 and -8 into -9. And now we can see there are some cancellations. So 9 minus 9, that cancels out. And once I cancel out the 9s, I can see there's an h in every single term in this fraction. So if there's an h in every single term, we can cancel one h from each term. And I'll write down the limit we have left to solve here. Equals limit h goes to 0 of 6 plus h over 1. And now we can use the direct substitution property because this is defined at h equals 0 now. So I'm free to just plug in 0. So I get 6. And so that would be, remember we are calculating the slope of the tangent line. Okay, so I found the slope of the tangent line at 3, 8. However, this question is not just asking for the slope, it's asking for the full equation of the tangent line. Tammy's got them. Yeah. So now I'm going to be creating the equation. So for an equation of a straight line, we just use any of our straight line formulas. You can use the point slope, slope intercept. In this case, we have a point on the curve, which is 3, 8. And we've got the slope. So I'm going to use the point slope formula. So I'm going to label this here, equation of tangent line. So I'm going to use the point slope formula. Oops. I'm plugging in the slope already. Mx minus x1. And so it would be y minus, so the y value is 8, the m is 6, and x1 is 3. You can also write it in the, you can convert it to slope intercept. This example, it doesn't specify which form to write your equation in, so any form would be fine. So this would also be correct. So I'll just highlight them both. And I'm going to show you what that looks like on an actual graph so you can visualize this. Like, what did we just do here? So first thing I'm going to do is just graph x squared minus 1 and that 0.38 and show you what that looks like. So here's x squared minus 1 and here's the 0.38. Okay, and I'm going to type in that formula I just created. So we wrote y minus 8 equals 6, x minus 3. And look, I've got my tangent line. So that's what we just made, is the equation for that purple line there, which you can see exactly follows the shape at that point. It just crosses the curve at that 1.3, 8 and has a slope of 6. Okay. So this is one way you can actually check your work when you're working at home, is you can use have Desmos open alongside and just plug in your answer and see if it actually makes sense on the graph. Let's say I calculated wrong and I got -2 as my slope. You can see this is not the tangent line, right? It looks quite different, doesn't follow the shape of the graph. Okay. Great, so that is example 1 completed. Now we're going to look at one application of finding the slope of a secant line and tangent line, and that's in physics when we're looking at position functions. So it says, suppose your f of t represents the position function of an object. Okay, that could be height, that could be distance, something that describes the position. Okay, then to get the velocity, which is just the speed with a direction attached, to get the average velocity, you would find the slope of a secant line between 2 points. Okay. To get the instantaneous velocity, like if you're in a car, that's like what your speedometer is reading at that second, then you would be calculating the slope of the tangent line. Okay. So let's just do that in an example. So just as a reminder, we're looking at position functions here, and then the slopes would be either the average velocity or the instantaneous velocity. Okay. So here's an example where we are given a position function. So we're looking at a ball that's dropped from the CN Tower, and the height of the ball is described by this position function. So I'm just going to label it so that's clear. So you can plug in a time t and it would tell you what the height of the ball off of the ground at that time. So for part A, we're finding the average velocity. So we're using the secant line during the first 5 seconds. Okay, so for average velocity, we're using the slope average velocity in first 5 seconds would be finding the slope of the secant line between t equals 0 and t equals 5. Okay? Right hand. So that makes sense. Okay, so we can do that just by doing rise over run. So or you can use the secant line formula. So it would be f of 5 minus f of 0. That would be the change in y values over the change in x values, which is 5. Okay, and you would plug it into the formula. So you get 490 minus 4.9. Oops, what's that? 9 times 5 squared minus f of 0, which is 490 all over 5. And you can just believe me when I write down the answer here. So that's 367.5 minus 490 all over 5, which is negative 24.5. Okay. And to look at the units, so we see that the y values are being measured in meters, and the t values are being measured in seconds. The x values are in seconds. So this is meters per second. So this answer would be in meters per second. And if you're wondering why it's negative, that's because the ball is falling downwards. So the sign tells you the direction of the speed. So or the ball. So the ball is traveling in the downwards direction, so that's why it's negative, and the speed of the ball is 24.5 meters per second. Okay, but let's say we want to know what the actual speed is right when the ball hits the ground. So in that case, we need to find the slope of the tangent line. So if we want to know the ball's speed when it hits the ground, first of all, we need to know when it actually hits the ground, what time that is. When does the ball actually don't tell us in the question when the ball hits the ground, right? But we can use that position function. When the ball hits the ground, its height would be 0. So we can just solve this equation to find that time. So we're not finding the speed yet, or the velocity yet. We're just finding the moment. We want to know what time it actually hits the ground so that we can use that formula we have. So I'm going to just isolate t here. So I'd have 4.9 equals, t squared equals 490. T squared equals 100. T would be plus or minus 10, taking the square root of both sides. You can't have a negative time, so t equals 10 seconds. Okay, so that would be our a value in our equation. We're interested in finding the velocity at 10 seconds. So we're going to use our formula for the slope of a tangent line when a equals 10. So we're taking the limit as h goes to 0, f of a plus h, so in our case 10 plus h, minus f of 10, all over h. Okay. And we're going to plug in 10 plus h and 10 into the formula. So we get, when I plug in 10 plus h, I get 490 minus 4.9 times 10 plus h squared. And when I plug in f of 10, I get 0 all over h. Okay, and again, we have to use our strategies from section 2.3 to solve this limit because I can't plug in h right now because it will be divided by 0. So I'm going to expand that bracket there. So h goes to 0, 490, hopefully I can fit it all in this line here, minus 4.9, and I get 100 plus 20h plus h squared all over h. And I can expand that even further by multiplying the 4.9 into the bracket. So I get limit h goes to 0, 490 minus 490 minus 98h minus 4.9 h squared all over h. Notice the negative also multiplies in, so all those terms are negative. So we have some nice cancellations. The 490 and the negative 490 cancel out. And once you do that cancellation, there's an h in every single term in this fraction, so I'm free to cancel one h from every term. And I get limit as h goes to 0, negative 98 minus 4.9h. And now this is defined at h equals 0, so I can just sub that in. So negative 98 minus 4.9 times 0, I get negative 98. And so my velocity at 10 will be negative 98, and remember we're measuring in meters per second. Okay, so for a word problem, you always need to include the units, and they'd be the same units as you would have for slope. And again, it's negative because the ball is traveling downwards. Okay, that's it. So I have a quick note about the required questions here. So you're doing 3A and B, 7, 9A and B, and 13. The book actually has 2 separate formulas for slope of a tangent line, and we're just using one of them. So ignore the book when it says use definition 1 or equation 2. You can just use our formula that we have here in our notes. And then there's the extra practice questions as well.